Right, okay. We are moving on to the next talk, which is given by Ionescu. The topic is about lightweight and efficient cloud services. Alex.
Thank you. Writing distributed systems is difficult, even in the case of simple systems. As an example, I will consider a simple system with like 3 nodes that I will refer to as locations, L1 to 3. So the traditional way to write a distributed system is just using networking primitives like send and receive. The problem with this approach is that it's very easy, for example, due to mismatched control flow between these locations, to end up with one location running a receive, whereas while like the other end is not sending, or the vice versa, which leads to deadlocks and other similar issues. And the fundamental reason for this is that for each one of these nodes, even though they're part of the same kind of large system, we need to write a separate program that's completely independent. And choreographies and choreographic programming aims to solve this issue. This is a different programming model for writing distributed systems that has actually been around for a while. It's been introduced by the World Wide Web Consortium in 2004, but more recently it has started picking up more pace. Coming back to the example, how choreographies help here is that using choreographic programming, you can define one single big program that encapsulates the behavior of all nodes in the system. So you get like a global view of the system. And choreographies also provide some higher level operators that you can use for communication. So instead of having to choose between send or receive, you can just say in your program that L1 sends a piece of data to L2. And there is an automatic process called endpoint projection, which is going to take this big program and kind of specialize it for each node in the choreography. And it's going to compile down that higher level operator into the appropriate networking primitive at each occasion. The thing this gives us is deadlock freedom by construction, which is a really useful property to have. So if you write a choreography and it compiles, you have a guarantee that the resulting system is going to be deadlock free. And we're going to be focusing on writing choreographies in Haskell here, which is doable using the HasChor library, which was introduced a few years ago at ICFP. It implements choreographies as a monad in Haskell, so it plays very nicely with the rest of the Haskell ecosystem. And we're just going to quickly go over the HasChor API. The 2 main types are the choreo monad and this A at L type, which represents what's called a located value. So again, a choreography is a global view of a system, but some pieces of data are only going to be available at one node, and they are represented using these located values. And HasChor provides some higher level operators for communication using these located values. For example, this squiggly arrow simply sends a value from one location to the other. So it just takes an A at L1 as input and gives you back an A at L2. The location itself is represented as a proxy because these L's that we've seen so far, they are basically type level tokens, type level strings representing the locations. So the proxy is used to give you like a value level handle to the location. And there's also a locally operator, which this is basically how located values are created. You run a local computation at a single location, and that gives you as output a value at that location. Just to give a quick illustration, here's again a system where we have a value at L1, and using this operator we can send it to L2, and we can notice that its type changes to A at L2. And our work builds upon HasChor, and our motivation is that we want to use choreographies to implement network protocols, because deadlock freedom by design is a great property, and of course we want our network protocols to be deadlock free. And specifically the protocol we are considering is that of a data clean room, which consists of many clients that wish to perform some shared computations on their datasets, but they don't necessarily trust each other to share the datasets between themselves. So there is kind of like a trusted server in the middle that the clients communicate with, and that one performs the computation and distributes the results. And this can be combined with things like trusted execution environments to ensure security. Here is a kind of simplified diagram for what a protocol like this might look like. So on the left here we have the potential clients, in this case hospitals, and here we have the server. So in this schema, sorry, in this diagram, the protocol first begins by the clients sharing their own data schemas to the server, and then the server is going to compute like an aggregated data schema containing all the columns, and then just distribute it back to the clients. And then each of the clients says what kind of queries they wish to run on the aggregated data. Then there's going to be an agreement phase where a client could say that they don't agree with what this other client wants to run. So the protocol could end here if the clients don't agree. But if they do agree, then they actually proceed to send their data sets to the server, who then computes the queries on the aggregated data and sends the results back. Now, it would be great to implement this as a choreography, but using HasChor and the existing API, the programming model is a bit restrictive because the communication is kind of simultaneously too granular and not granular enough, because HasChor's communication is kind of all or nothing. You either send a piece of data just from one location to the other, or you have to broadcast it everywhere, which we'll see a bit later for branching. And also, HasChor is kind of optimized for running a choreography with a fixed set of participants, so it's kind of difficult to define a choreography that you could run with, today with 50 clients, tomorrow with like 100 clients. So our contribution is called the CloudChor, which is a set of extensions for HasChor, which adds some new operators and primitives to make these kinds of protocols easier to write. The main new concept we introduce is the notion of a multiply located value, which enables these more complex communication primitives. We will see later how we optimize HasChor's branching with static analysis, and how we make it easier to run choreographies with like dynamic and configurable participants. And lastly, we also formalized the semantics of HasChor and of our extensions to it. So the first new concept we introduce is multiply located values, which basically allow you to treat a bundle of these located values that could be at different locations. This lets you treat them as a single unit that you can then manipulate easier. And using this, we can implement some more advanced communication primitives. And what's nice about this is that this doesn't require any kind of modifications to the core of HasChor. We can just implement it as some extra functions, basically essentially lowering to HasChor's primitives plus some generic programming techniques. So we introduced this new data type, which we just called @@. But this one on the right, instead of having a single location, has a type level list of locations. So a value of type A at LS means that this value is distributed, like basically each location in LS is going to have one piece of this value. And for representing these at the value level, instead of just using a single proxy for one location, we use another generic programming type, this NP, which is basically a heterogeneous list of a proxy for each location in LS. So this is, kind of equivalent to just a list of a proxy at L1, L2, and so on for every location in LS. And using these multiply located values, we introduce a number of new operators. The first one is for what we call one-to-many communication or scattering. So if you have a located value at one location and you want to send it to multiple destinations, using this operator, you can do exactly that. And the output is a multiply located value at those destinations. And you can see we use the NP proxy here to represent the destinations. The kind of flip side to this is many-to-one communication. So when you have values located at, you have a multiply located value already that's distributed across your system, and you want to send all of them to a single destination, you can use this gather operator, which just accumulates them all into a list. And the output here, the type looks a bit complex because it's again using an NP of a weird generic programming type. This one is basically just a list that is guaranteed to have the same length as the length of LS. And tracking this length of the list in the type allows us to later on, with a different operator, send these values back to their origin one by one with this pointwise communication. And lastly, we have a multiple-located analog to HasChors locally, which we just call multi-locally, which lets you run local computations in multiple places at once, producing a multiple-located value. And using these, you could implement a protocol like the data cleanroom in a much easier way. For example, all of those, the steps in the protocol where we had many clients sending their queries or their schemas to the server and then the server distributing it back, those very nicely map to the operators I've described so far. And once you have that choreography written, it still relies on all of these type level indices, which normally would be pretty difficult to kind of instantiate dynamically. But using generic programming, we can also write some easy to use functions that let you just using a dynamic list of strings, basically turn that into a type level list of locations that you can instantiate your choreography with. Next up, let's look at propagating choice in choreographies in general and in HasChor in particular. Branching in choreographies is a bit tricky because to ensure this deadlock freedom, you have to ensure that every node in the location, whenever there is a branch, they all take the same branch. Otherwise, it might be that in one branch, one location should be sending a piece of data, but because it took another branch, it doesn't. Which means that the value that you're branching on or the decision that you're branching on has to be broadcasted to all members of the choreography. In HasChor, this is done with this cond operator. So here we have a small choreography where at location L1, we are locally computing some data that we then want to branch on. So we do cond from L1 with B, which means that L1 is going to broadcast B to everyone in the choreography, and then they are going to all run this function here with B. And here we have a branch. If B is true, then L2 is going to send something to L3. Otherwise, if it's false, it's going to send something, L2 is going to send something to L4 instead. And what's crucial here is that everyone runs this. Even, for example, if you have an L5 in this choreography that is not mentioned here at all, L1 will still send the B to L5, and L5 will still run this code, but it will just be a no-op. But we still have some network communication overhead here. So we, in our contribution, we also try to optimize this. Again, looking at the cond function from HasChor, we see in its type signature that it has the value to be broadcasted, and then the function that every member in the choreography runs. And yes, everyone in the choreography runs this function, even though they might not be involved in it. For example, in a protocol like the one we've seen so far, you might have some error handling where when the client is sending the data set to the server might check that it conforms to the schema. And if it doesn't, it might send a message back to the client. In this case, you don't want to message every other client, for each client's particular error handling. So to make this more efficient, we have to find out somehow who is involved in this function to only communicate the branched value to those locations. And we do this using a technique from partial evaluation called the trick. And coming back to the example, how we apply the trick in choreographies is we basically enumerate the possible values of the scrutiny of the branch value, and we just apply this function to all of those values, collecting all of the locations that we see along the way. And then that's how we can build a set of involved locations. With this, we introduce a new operator that we just called cond underscore, implementing this kind of optimized branching. It introduces the two new constraints on the scrutiny, that it has to be enumerable and bounded, so we can actually enumerate all the values. And there is one more difference here. The classic cond does not return a located value. It returns like a regular value, which means a value that's present everywhere, because by definition, everyone is going to run this function, so everyone can build a B. But with this cond, that's the main point of this cond, is that not everyone's going to run this function, so not everyone can build a B. So we cannot just return any value. It's going to have to be a located value, and since the only location that we know for sure is going to run this is the one sending the value, then the output is also going to have to be located at the sender. And lastly, we also provide formalization for the semantics of HasChor and also our optimized cond. Note that we don't formalize our other extensions because they just lower to HasChor's primitives. So their correctness basically follows from the HasChor primitives. We proved soundness and completeness of the endpoint projection process, which means that this low-level kind of specialization and compilation step preserves the high-level global behavior of choreographies. And using this, we can show that HasChor and our extensions indeed are deadlock-free. And our proofs are based on the principle of confluence, that if you have a kind of a network system that could reduce some locations in a different order, the order in which it does so doesn't really matter. So to conclude, we've seen how choreographic programming works and how it works in Haskell with HasChor. It provides deadlock freedom by construction, and it can be useful for designing network protocols, but it does have a few limitations. And we introduced CloudChor to try to address these limitations by employing multiply located values and by optimizing the implementation of branching. And and also we made it easier to run choreographies with configurable participants. And we also provide a formalization of HasChor and of our extensions. With that, I will thank you all for your attention.
For questions?
Have you started to build systems with this? Do you think this is it? Is this the end of extensions for HasChor, or what else is left?
Yeah, we have started building something with it, but I don't think it's the end necessarily. It's the first step. And there's also some concurrent work extending HasChor in a few different directions.
Thank you for your presentation. And I'd like to ask if you have a broadcast primitive or something like this, because your primitive explicitly enumerates the participants when you do multicasting. So do you have broadcasting instead?
Broadcasting as in just send it to everyone?
Exactly.
Well, you can use this for broadcasting. So if you make this function ID or pure, you essentially have broadcast.
I see. Thank you for your clarification.
So to clarify, we don't replace this operator, we just introduce a new one. So you can use both in the same choreography.
Thanks for the talk. Distributed systems tend to be distributed because they also have certain, at least crash faults. Can you accommodate a certain crash fault model, particularly when it comes to broadcasting, which is very sensitive to that, or multicast as you're adding here? Mm-hmm. How's it help build crash fault tolerant systems? Yeah, so that I guess depends on the kind of lower level network layer that you'd have underneath these choreographies. That's something that I think you'd have to fix to implement like fault tolerance at that level.
So I have a question about the use of Haskell. You mentioned the challenges in Haskell you have to address in the library, and what are the benefits of using Haskell?
Of using, sorry, HasChor or Haskell?
Haskell.
Haskell,
Yeah.
the language.
Yes.
The benefit of Haskell over other languages is well, first of all, the advanced type system. Like the fact that we can track locations in a type system is not something we could do, or not, at least not easily in other languages. And also the fact that Haskell is a pure language with tracked effects. So one thing I've kind of glossed over here is that when you're running those local computations, you can run some locally effectful computations. But the choreo monad tries to kind of hide that away and control effects, such that when you have a choreography, you can't have effects that interfere with like the network communication and so on.
For your variant of cond on this slide, you said that you collect the list of participants from your functions at first, and then you broadcast to everyone in that group. But that's not reflected in the type of cond. Is it possible with a better type system, better in quotes, to track that within the type of cond? And if you could, would it be useful?
So in other words, to like track the participants in the type. Yes, it's possible, and actually there is some work that's doing that, but it's doing that in Haskell is pretty painful. And also we tried to stay, one thing maybe I didn't stress out is that all of our extensions are backwards compatible with HasChor, whereas if you were to try to do something like that, you'd have to change the API quite drastically.
Right. Okay. Let's thank Alex again.
Thank you.